This video is going to be our second look at the method of undetermined coefficients. I just want to work through these examples. So if you missed the first video, go back and watch that where I outline the step-by-step procedure that we're going to follow as we look at these three examples. So let's go ahead and start with this first one. All right, what we want to do is solve the equation y double prime minus 4y prime plus 4y equals 1. So here we have this constant right-hand side. That's what we're going to be able to address with the method of undetermined coefficients. All right, as we said in our first video, the first step is to find the homogeneous solution y sub h. This is going to be the function that solves the homogeneous problem that we associate with this. That's going to look like y double prime minus 4y prime plus 4y equals 0. Okay, so we want to find the general solution for this homogeneous second-order linear differential equation. To do that, we're going to revert to the characteristic or auxiliary equation, r squared minus 4r plus 4 equals 0. This factors. We have r minus 2, r minus 2. That means that we are looking at the situation of having one real repeated root. So r equals 2 is a repeated root. We've discussed how to write down the solution to this kind of homogeneous problem before, so let me just jump straight to it. Y sub h of x is going to be built out of two pieces. The first one is c1 e to the 2x, where this 2 comes from that root r equals 2. Then because this is repeated, our second component is c2x e to the 2x. All right, let me pause here for a moment just in case you need to revisit what the solution looks like when you have a repeated root. Our next step, which I'll pick up with in a minute, is to find a particular solution to the differential equation as it was given to us. Moving along now, the second step is to guess a solution, a particular solution which would solve the equation with that forcing of 1 on the right-hand side. Okay, so we just have a constant forcing function. That means that I'm going to guess that the form of the particular solution looks like a generalized version of that right-hand side. The right-hand side is a constant, so I'm going to guess a constant. Let me just name that c sub 3. Now, our third step is to plug this constant into this differential equation and see if we can make it work. In this context, making it work means see if we can find a value for c sub 3 that, when plugged into this differential equation, makes the whole thing true. All right, so step 3, plug y sub p in. Let me rewrite everything in terms of the particular solution y sub p, and then we will substitute in just this constant. Okay, so we have y sub p double prime minus 4y sub p prime, there we go, plus 4y sub p. Okay, the derivative and second derivative of a constant are 0. So we're going to have 0 plus 0 plus 4 times c3. Okay, that is what the left-hand side of our differential equation looks like when we substitute in this form of a particular solution. But now let's see. We have 4c3. We want it to be equal to 1. That means that this constant can now be given the explicit value 1/4. All right, that wasn't so bad because the constant derivatives just vanish and we were left with a pretty nice equation for c sub 3. We can now write down the general solution. So the method of undetermined coefficients brings us here. The general solution to this differential equation is y of x equals the homogeneous part. Oops, that's supposed to be an h. Okay, I'm gonna try that again. The homogeneous part plus the particular solution, which is going to look like c1 e to the 2x plus c2x e to the 2x plus the particular solution of 1/4. That wraps up this first example. What you probably noticed a minute ago was that all three examples in this video have the same left-hand side. That's going to allow us to immediately write down the homogeneous solution for the next two examples so that we can skip step one. The reason why I think that's a good idea is because we've already spent a lot of time finding homogeneous solutions. That's not what's really new with the method of undetermined coefficients. So in the next two examples, what we can focus on are steps 2 and 3. For our second example, the forcing function on the right-hand side is 3x squared plus 5. Since we already know the homogeneous solution, let's go ahead and guess the particular solution. It's going to look like the right-hand side. The right-hand side is a degree 2 polynomial, so I'm going to guess a sort of generalized degree 2 polynomial. To do that, I'm going to use the coefficients a, b, and c. I just think that's easier than c3, c4, c5. So let's write that our particular solution will have the form ax squared plus bx plus c. That is the function that we are going to try. And when we plug it in now to the differential equation, what we hope is that we can find numbers for a, b, and c to give us a specific function. Okay, so let's plug this in. I think I will skip writing out yp double prime minus 4yp prime plus 4yp and just go ahead and put this right in. So we are going to have ax squared plus bx plus c. Need to take the derivative of that twice and then subtract off 4 times its first derivative, ax squared plus bx plus c. Let's see, prime, there we go. And then add to that 4 times this particular solution. Okay, I'm definitely going to run out of room over here, so let me just work down. Let's see, if we take this quadratic and differentiate it twice, this will go away. This would turn into b and then to 0, so we will have 2ax2a. Okay, I apologize if I did too much without writing it down there, but basically if you differentiate that quadratic expression twice, you're just going to be left with 2a. Then minus 4 times the first derivative is going to be 2ax plus b. And then let's go ahead and distribute here. We have 4ax squared plus 4bx plus 4c. What we want to do now is group like terms together. We have a quadratic term, just one. Then we have minus 8ax plus 4bx. Oops, plus 4bx, there we go. Those are the first order terms. Then for constants, we have 2a minus 4b plus 4c. 2a plus 4c, yes. We want to do coefficient matching. This is a quadratic, and we would like for this to be the same thing as 3x squared plus 5. So that means the quadratic term should be 3x squared. The first order term should be 0x. We don't have a first order term there, so we want to think of the coefficient on x as 0. And then lastly, the constants need to add up to 5. This is going to give us 3 equations for the 3 unknowns, a, b, and c. So let me do that here. Okay, so what are we going to do with the quadratics? Well, we know that 4a should be 3. If you look at the coefficients here, 4a and 3. So immediately we get that a is 3/4. For the first order terms, Negative 8a plus 4b needs to be 0. Let me move 8a to the other side and simultaneously divide by 4 so that b is 2a. A is 3/4. That makes B 6/4, which is 3/2. All right, then our first order terms, sorry, 0th order, constant terms is what I meant to say. We have 2a minus 4b plus 4c equals 5. Let me go ahead and plug in the values that we know for a and b as I write this down. So 2 times 3/4 minus 4 times 3/2 plus 4c equals 5. There we go. Okay, that's 5. Let's see. Let me move to this and this to the right-hand side. Leave 4c alone. I'm going to write that here. 4c is going to be 5 minus 2 times 3/4 is 3/2. Let's see, that's minus. This is going to be plus. And then plus 4 times 3/2 is 12/2. So that's 6. Like that. All right, so overall, we have 11 minus 3/2. So that's what, 18/2? Write that down and check it. Let's check this. Okay, 11 is 22/2 minus 3/2. Okay, yes, so that is 19/2. Knew it felt kind of strange as I was saying it. That should be 19/2. All right. Divide both sides by 4 now, and we get that C is 19/8. All right, we have found values for the constants A, B, and C. That's what we do with step 3 is we check our particular solution, and if it's a good choice that we made in step 2, then we should be able to solve for all of the constants. When we write down the general form, the only constants we want to see come from the homogeneous solution. Go ahead, write that form down. All right, hopefully this is what you wrote down. The general solution that we get with the method of undetermined coefficients is the sum of the homogeneous solution and this particular solution that we just worked out. So it looks like the homogeneous solution plus 3/4 x squared plus 3/2 x plus 19/8. We are going to move on now to working with these initial conditions. That's just the usual process of plugging 0 in for x, differentiating, plugging 0 in again. So at this point, we're done with the method of undetermined coefficients, but I will take you all the way through the end of this problem. Before we do that, let me make one remark, which is that we have this first order term here, but we don't in the forcing function 3x squared plus 5. The message is that when you have a polynomial right-hand side, when your forcing function is a polynomial, you need to guess from the highest power on down to constants. Don't skip anything. So if your inclination was to write down just ax squared and the c terms, we would be missing information that we actually need. So with polynomials, make sure you include any terms that perhaps get skipped when you look at the forcing function. All right, I've copied over the general solution. Let's go ahead and plug 0 in for x. We know from what we are given that y of 0 should be 0. When we plug 0 in for x, luckily most of this is going to go away. So if you look at this and it fills you with a sense of dread, it did for me as well. But luckily, plugging in x equals 0, we're left with c1 times 1 plus 0 plus 0 plus 0 plus 19/8. So actually, it's pretty nice. That tells us immediately that c1 is negative 19/8. We only have one constant left to solve for. We have to take the derivative. So a little bit more work left. But when we take our general solution and differentiate it, how about I go ahead and use the value of C1 that we just found. So we will have 2C1, that's negative 19/4 e to the 2x. Okay, so what did I do? I differentiated this. 2 came down. 2C1 is twice negative 19/8. That gives me negative 19/4. Okay, differentiating the next term, we need to use the product rule. Differentiate the first part, you get C2 e to the 2x, and then plus 2C2x e to the 2x. You might already be anticipating that this term is going to vanish because of the x, but let me just be complete and write it down. Then we will have plus 2 times 3/4, so 3/2 x, plus 3/2 plus 0. Okay, so that's the first derivative. Y prime at 0 is 1. When we plug in x equals 0, we'll get negative 19/4 plus C2 plus 0 plus 0 plus 3/2. All right, let me collect everything on one side. I'm going to leave C2 on the right, but write it on the left. So let's see, move these over. All right, 4/4 plus 19/4 minus 6/4. Okay, so I moved the 19/4 over, I moved the 3/2 over, and then I gave everything a common denominator of 4 so that I can say that 4 plus 19 is 23 minus 6 is 17. So overall C2 is 17/4. And that's it. Now we've solved it. I'll write it out one more time. Quite a few terms to write out here, but the solution to our initial value problem is C1, so negative 19/8 e to the 2x plus 17/4 x e to the 2x plus 3/4 x squared plus 3/2 x plus 19/8. Okay. We have one more example to do where we have the same left-hand side for the reasons I already mentioned. We know how to find homogeneous solutions. Let's not spend too much time there. The right-hand side is going to look a lot like the problem we just solved, but there's an extra term. So in our next example, we are going to say that the forcing function is e to the x plus 3x squared plus 5. So here I'm repeating 3x squared plus 5 because we can actually reuse some of the work that we did. We don't have an initial condition problem this time, so we will go back to this and we will say the homogeneous solution is going to be the same because it's the same left-hand side. But we will also use sort of addition of solutions approach to the right-hand side, where we will say that this quadratic solves the 3x squared plus 5 part of the forcing function, leaving us only with the exponential function to investigate. Okay, we'll do that in a minute. Let me step aside so you can copy this down, and then I will erase everything. I'll put up what we already know. So actually, I'm going to leave that y of x at the top. Yeah, we'll just leave that. And then we will address this new component on the right-hand side. All right, let's wrap up with this example where we have almost the same equation, but I've changed the right-hand side to e to the x plus 3x squared plus 5. This solves most of the equation. We just need to account for that e to the x term, and let me explain why. For step 2 of our method of undetermined coefficients, what would we guess for the particular solution in this example? We would guess yp of x equals some generalized looking version of that forcing function, which in this situation is going to look like, how about I call it d e to the x plus ax squared plus bx plus c. And we want this to match up with e to the x plus 3x squared plus 5. What would happen though if we took this whole approach is that when we plug in our particular solution and we start matching terms to solve for these coefficients D, A, B, and C, this would match up with this, whereas this would match up with this, and it would be the exact same coefficient matching that we did a minute ago. So what this means is that the work we did to say that 3/4 x squared plus 3/2 x plus 19 over 8 gives us the particular solution when the forcing function just looks like 3x squared plus 5, that's still going to work here. We just need to add, some multiple of e to the x. Okay, so we just need to work with this and this. Okay, so for step 3, what we will say is d e to the x prime prime minus 4 d e to the x prime plus 4 d e to the x. We want to simplify this now and ultimately set it equal to e to the x. All right, differentiating e to the x looks like e to the x, so that first term is actually just going to be de to the x. Similarly, the middle term is just going to be minus 4 de to the x, and then plus 4 de to the x. Okay, so overall, after we simplify the left-hand side, we're just left with de to the x. We want that equal to e to the x. So d equals 1. And we're done. So it looks like a big problem, but we did so much of the work already that now I can say that the general solution to this second order problem is what we had before plus one more term, 1 e to the x. Okay, so when your right-hand side is a combination, in this case, it's a combination of an exponential function and a polynomial, you can do those separately. So you can solve the exponential forcing and you can solve the polynomial forcing, then you add them together. All right, that wraps up this video. I have more examples in the next video.